Well, let's start.
Sure. Can I get a water?
Water? Yes. Maybe. Yes.
Yeah, it's a long presentation. Yes.
Do you want the water?
No, I don't. Okay, sorry. I'm using the device for the
They say it's working, so streaming is live. Okay, so I'll make a short introduction in Spanish and I should
Sure.
So, bueno, benvinguts a tots aquesta tarda. Gràcies per venir, gràcies a cerca d'OpsGenie, als amics de Skyscanner per cedir-nos l'espai. Avui farem per primera vegada una doble presentació. Fins ara sempre fèiem només una presentació, però avui tenim dues presentacions, una que farà el cerca i l'altra que farà Radek, oi? Tots dos, com no són d'allí, les presentacions seran en anglès i bueno, per primera vegada també estem fent streaming de la sessió, que bueno, tinc aquí el portàtil que està apuntant cap allà, però que després a YouTube estarà el vídeo, que si algú vol buscar la presentació i el vídeo la tindrem allà penjada. So, Serhat, thank you very much for being here. Just let you introduce and go ahead with the presentation. Thank you.
Hello guys, my name is Serhat. I'm a software engineer at OpsGenie, and I came here at Barcelona for Atlassian Summit last week, and I'm here like 10 days now, and wanted to make a presentation about what we do with the serverless architectures at OpsGenie, and that's basically what I'm going to talk about today. And before I do that, I'd like to talk a little bit about OpsGenie because the use cases I'm going to talk about here is the ones that relates with the nature of OpsGenie, relates with what we do. Just a quick introduction. And so OpsGenie is an incident response orchestration solution, generally for DevOps and ITOps teams. We provide the tools and integrations, for you to design actionable alerts, on-call schedules, and escalations. So we notify users through lots of notification channels like SMS messages, voice calls, mobile push notifications, or chat applications like Slack, HipChat, and we are integrated with monitoring tools like Nagios, Radek, we have hundreds of integrations, and when something is wrong with your service, we are the ones that need to notify you guys. So we need to be up and running all the time. That's our requirement. Actually, that's not just a requirement for us. It's like a business critical requirement for us. So today, what I'm going to show you, some of them especially are related with this, this concern. And so my presentation have three main parts. First one is I will talk about a little bit about serverless, what serverless is, just to give you a quick introduction if you don't know yet. I'm assuming there are some people, And then I will go through some of the use cases. Actually, the main part is this. I will go through the use cases we have, how we use serverless architectures in OpsGenie. Then I will, point out some of the challenges we faced with serverless architectures and try to, tell you how I will solve them. So, what's serverless, or in other words, function as a service? So serverless is a little bit misleading word, as you can imagine, and it doesn't mean running code without servers, of course. There are servers involved, but these servers are abstracted away from you, so you don't have to worry about them, you don't manage them, and cloud providers manage them for you. It automatically scale. What I mean automatically scale, it's not just a buzzword like the other services. It literally automatically scales, and So another a big difference is that in regular applications you have like the long-running virtual machines, and these virtual machines, these applications are not updated if you don't deploy them again. If you don't make some changes, they are just keeps running. But in serverless or function as a service case, these applications are event-driven. So they start and stops executions for each request. And underneath, AWS Lambda or other serverless architecture providers runs containers. So it's totally transparent. You don't manage them, you don't see them. But there are some challenges that I will talk about later about running these containers underneath. And also, this starts and stops, starting and stopping between each request changes the pricing of the services. You really pay only for what you use. In EC2 case, in regular virtual machine cases, you pay hourly based, and you still have to generally you need to run your code continuously, so that you don't know when you are going to get a request from the customers. So, but in serverless, it's not the case. So one more slide about serverless, just to compare the cloud computing services provided by for example AWS, and in infrastructure as a service case, the equivalent of this service in AWS Lambda is EC2, and EC2 gives you a virtual machine. You will handle the runtime, installing the runtime, and all the other updates. It's up to you. In container as a service case, you need to handle your containers, not your operating system. One more layer abstraction, and Amazon ECS is a good example for this. And platform as a service is generally the ones that people confuse with the function as a service. In platform as a service, actually there are two main differences between platform as a service and function as a service. The first one is that in platform as a service, your applications does not scale automatically like they are in function as a service case. You still need to define some configurations, like when my instances reach 70% of CPU time, you add a new instance, etc. It does automatically, but you still need to have some sort of configuration, and it takes some time to provision a new server, like for example a couple of seconds. Generally it's not the case, but you can still experience some downtime during that time. And the similar part is that the runtime provided by the cloud provider like AWS. And in this case, you again upload a zip file, for example, or jar file to for your application. But in the platform as a service case, you again have a long-running application. You pay for the whole time you run your application. You don't know when the request is going to come, but you still need to run it. In function as a service case, your code just executes when the request comes and stops executing after the execution finishes. This is the two differences. So I will talk a little bit about AWS Lambda, then go to the use cases. So as I said earlier, serverless architectures are event-driven architectures. So you need to have some sort of events that trigger these these functions. In AWS Lambda case, AWS Lambda is very well integrated with Amazon's other solutions, and generally most used ones are like DynamoDB streams, Kinesis streams, and S3, and we are also using scheduled events a lot, and Amazon API Gateway also used a lot. Just it's to create an API endpoint, and then you can trigger AWS Lambda by using API Gateway service. I will not go over them one by one. Then we have some limitations that I need to I want to talk about. And as the serverless providers manages the underlying infrastructure, the runtime environment, so you just upload your code and it just runs. You don't have the choice to you cannot choose the language you want. They are provided by the AWS Lambda itself. So you have currently 4 options, but I think they are going to bring Golang etc. Soon. Also, they are bringing different versions of these applications, like Node.js. I think there are 3 versions running now. You can choose one of them. Java, Node.js, Python, and C# are available ones for now. And you have the limitation of maximum memory 1.5 gigabytes. So and also CPU increases when you increase the RAM accordingly. So and another limitation is the maximum execution duration per request. So your function execution needs to be needs to end at most 5 minutes. So if it's not ending and it's expected, it's not recommended to use serverless architectures. You just go with the regular way. So you need to know your use case, and if it fits the serverless case, it is important. And we have the limitation of concurrent executions. It is currently 1,000, increased to 1,000. It was, I think, 150 last year, so it is like increasing a lot, and I think it will continue to increase. And also, you can just soft limit is that so you can ask AWS to increase it to 3,000 immediately, and they will do it immediately. And still soft limit, I guess, and you can just ask them and to increase. So I will talk about what concurrent execution is more later. So I'm gonna just skip that for now. So some of the features I want to talk about today is the AWS Lambda features, VPC support. So you can run your Lambda functions inside of VPC to add additional layer of security, restrict them access to other services, etc. And we are running also some of our functions inside of VPC. I will show them in the use cases. So we have environment variable support. So just to you want your function to run differently based on some configuration variables. So you don't have to go to S3 or other services to get the data and act accordingly. You can just attach some environment variables and get them in your application easily. But if you have some sort of secret keys, you still need to use services like key management service, or you can still use S3, etc. We have something called dead letter queue. So you can call your Lambda functions is triggered from lots of event triggers I showed you earlier. So some of them are synchronous, some of them are asynchronous. For the synchronous one, you call the Lambda function. If something is wrong, you need to handle the exception yourself. But if it's asynchronous, you need AWS automatically tries twice, and if it cannot execute it correctly, if something is wrong, you are getting an exception. If you have defined a dead letter queue, it will send the payload and the necessary information to the queue so that you can pull later and try to execute it by yourself. But if you don't, define a dead letter queue, and let's say you are calling your Lambda function asynchronously using AWS Lambda SDK, it will just get lost if you don't have it. And we have function versioning and alias support. And we are using this one I will show you later. So you can assign some aliases, or version automatically increases, and you can use these aliases to call different versions of your Lambda function, and it will be very useful for the deployment cases, especially. I will show you later again. Also, a relatively new one, taking support. Just like in EC2 case, you have in EC2 you have key value pairs that you can assign to the virtual machines, so that you can query your EC2 machines and get do whatever you want with them. It's the same for Lambda functions, and it's relatively new one. So now I think this is the fun part. If you already know about serverless in general, and so our serverless stack, generally Java 8. At OpsGenie we generally use Java. Also we have some custom solutions, some let's say some small scripts written in Node.js and Python. But generally we have Java, and In DevOps team, we were using some custom deployment solution we wrote for Java because at the time serverless JS didn't support Java very well. They were just supporting Node.js, but now they also support Java, and we are moving to that direction and trying to use serverless JS where possible, if possible. So, I want to talk a little bit about reliability needs of OpsGenie. So, as I said earlier, we need to be up and running all the time because we are the ones that notify the users. We are the ones that need to be available all the time. So we are already operating, of course, on multiple availability zones, but even services with in this case it's S3, but 11.9 durability, etc. can't be trusted. You need to be ready for if you are running a mission critical system, etc. You need to be ready for regional failures as well. So for this one, we started operating on multiple regions recently, and if in case of something is wrong with the service, we can switch regions within seconds. But next step is to operate on multiple regions simultaneously. We are working on this right now, and most of the use cases I'm going to show you here comes from this requirement. So the use cases, first one, DynamoDB cross-region replication. So we use lots of AWS services like a lot, and DynamoDB is one of them. NoSQL solution for persistent storage, and we use DynamoDB for persistent storage as well. So our motivation in this use case here to replicate our data in DynamoDB to another region. There is a proposed solution for this in AWS GitHub account. It leverages KCL, Amazon's Kinesis client library, to get the data from DynamoDB streams and write it to you can write it to another region. But you still need to manage the EC2 machines. You need to scale them. You need to know the number of machines you need to run. You have the operational burden still, even if KCL abstracts away lots of things from you. Still, you need to manage those servers, but we didn't want to manage these servers. So here's architecture for DynamoDB cross-region replication. We have DynamoDB tables at the left here. So all these DynamoDB tables are connected to our Lambda function, and we call this replication stream listener Lambda. And all the data included in the DynamoDB streams receive data from the DynamoDB streams. So we get the data here, write it to another region. It's extremely simple. It's just like 15 lines of code. Get the data, put it in another region, and the records are ordered. So we don't have to hit the DynamoDB again and see if it's the latest version of the record. It's extremely simple, and we don't have to manage the servers. And AWS automatically creates Lambda functions for each partition for the DynamoDB table. I will talk about this later too in another use case in detail. So another use case we have, it's currently in progress. We are experimenting on this one, reporting, and I think it will be it is close to be on production, but it's not live yet. So our motivation is to create a robust architecture with minimal effort. We didn't want to learn all the fancy stuff with the big data zoo, and we didn't want to spend all the time to learn all these tools. This is one motivation, one of the motivations. Also, we wanted to have SQL-like aggregations and wanted to have some flexibility to query our data. So for this, it can change, but for this we have sources like AWS Lambda, by using general SDKs, putting data to Amazon Kinesis Firehose, maybe Kinesis Stream, EC2 machines, generally from using SDKs, Kinesis Firehose SDKs. We put some data, against firewalls, and firewalls automatically writes data to S3, and a Lambda function called Lambda function gets the data from S3 triggered by the S3. Get data, partition the data for each customer, and converts it to JSON format, and writes it to another S3 bucket. So in this case, we could have still triggered this Lambda function with the S3 events, but we didn't do it because the nature of org format requires bigger files to make it faster, and so because of the requirement org format requirement, so there's another Lambda function called org format converter, queries the data in S3. It runs periodically using Amazon CloudWatch events trigger, and gets the data and writes to another S3 bucket in org format. Then, by using Amazon Athena service, it's relatively a new one as well. We can query the data in S3 easily, and it's case automatically you can query directly from the S3 by using the Amazon Athena service. This is still in progress. So another use case we have is DynamoDB autoscale. So DynamoDB is extremely scalable service, but you still specify some read capacity or write capacity to the table, so that you don't want to so that you don't pay a lot for these tables, and you need to increase the read and write capacity if necessary, or decrease again if necessary, to avoid read and write throttles, provision throughput exceptions from DynamoDB. So another requirement we have here is migration. So let's say we are changing a table's structure, so we need to increase the read capacity here, because we are going to query the DynamoDB table and write it to another DynamoDB table. We need to adjust the read and write capacity for our needs, so that we don't get throttled. These two requirements here. So I need you to focus on this one for now. Autoscale Lambda. This is the main Lambda. It does the job. What it does is to query Amazon CloudWatch metrics to learn more about the DynamoDB tables usages, and also by gets the related metrics. By doing that, it needs to decide if we need to increase or decrease read and write capacity of the DynamoDB table. So to do that, we have another table and containing some data about for each table, so like minimum read, maximum read for the table, or update threshold, etc. We have some configuration, let's say configuration data about the table. So these Lambda functions get data from the metrics and knows the table's configuration variables like minimum read, maximum read, etc. Then it decides if it needs to update the DynamoDB table or not. So, but there's a custom logic here. It's a little bit smart, because you cannot downgrade DynamoDB table more than 4 times a day. There are some limitations. You need to think about these limitations while increasing or decreasing DynamoDB tables, read and write capacities. So this Lambda function considers these cases. Also, we have another Lambda function called DynamoDB alarm setup. So actually, you might wonder, why execute this periodically and get the data from the CloudWatch, but not use DynamoDB alarms from the Amazon CloudWatch? Because DynamoDB CloudWatch alarms notifies you a little bit late. You can be late, it takes like 2 minutes, and you still get throttled. That's why we can't do it, but we still have DynamoDB alarm set up just to to be notified if something is wrong. And we have another Lambda function creating these alarms for let's say we added a new table. This Lambda function automatically creates the necessary CloudWatch alarms for us. And for example, we update a table's read and write capacity. Also, we update the necessary threshold. We update the necessary Lambda alarm as well, so that we don't get notified for nothing. And in this case, we we are hitting the read capacity. So by using our CloudWatch integration and an alert is created in OpsGenie. OpsGenie sends notifies necessary on-call person. Also we send a notification to, in our case we use Slack. We send a notification to Slack, and we can acknowledge clause or act on the alert on Slack. And let's go back to the second motivation we have is to adjust the capacity for the migration needs. So for this, we have a slash command in Slack, something called DynamoDB table name, increase it to something like 25, let's say. We write it and it triggers an API gateway endpoint. Then API gateway endpoint connected to the Lambda function called config updater Lambda. So what this Lambda function does is to just update a row in DynamoDB table, config table. Then this DynamoDB table triggers our autoscale Lambda function through DynamoDB streams trigger. So then this Lambda function can update the DynamoDB table. So that's it. So another use case, actually we didn't move this to Lambda yet, but we are going to do it. We are doing it very soon. We are going to do it. Currently, so basically our basic need is to index our data to Elasticsearch, and also we need our Elasticsearch data available in every region. So, and by doing that, we don't want to include this logic like if this operation, if you are operating on this region, use this SDK, etc. So we don't want to put this into the business logic. And this is another motivation for doing it this way. We were in the old architecture, now it's gone, but we were using SQS. But as we operate on multiple regions, and SQS, in SQS, if you want to, you need to send your data to all the regions you operate on to just to index them in other regions. So we didn't want that. So currently we are using KCL and a virtual machine running by using client Kinesis client library. We are connected to DynamoDB streams, getting the data and writing to related Elasticsearch instances. And the architecture we are going to use soon is that we have Lambda functions running. We don't manage any servers. We don't in our case we need to adjust the number of instances we run for the KCL to work properly, not to waste any resources. But in Lambda case, it just automatically creates a Lambda function, create a Lambda function, runs a Lambda function for each shard. So let's say you have 4 shards for a Kinesis streams, for a Kinesis stream. So it runs 4 Lambda functions concurrently for each shard. It's extremely important because in KCL case, let's say you are running 5 virtual machines, only 4 of them consumes these shards one by one, and the one is the 5th one is just works for nothing. But in this case, you don't see the sharding. You don't have to manage the KCL, etc. You just DynamoDB or Kinesis automatically gives you the record and creates a Lambda function for each shard. So you can write your data. In this case, we are writing to Elasticsearch. Also, I think we are writing to InfluxDB, for example, but you can write to any other data source or whatever you want. In this case, it's rather a generic architecture. So I think this is one of the killer use cases, lifesaver, let's say, lifesaver use case for us, because some of our customers, for example, want some sort of custom solutions, and these custom solutions are generally very specific for the use case, so we cannot include this logic into our application. So for this kind of situations, we generally write a Lambda function, and this Lambda function, comes with some benefits. The first one is customers do not need to manage servers. They might not know. How to create a virtual machine, upload your code and run it. Also, we have a separate AWS account to run these custom solutions. Sometimes we run it. Sometimes if customer wants to run it, we give the function to them and they run by themselves. But generally we do it. So also it's again because it's easy to deploy for customer or for us. It's just as generally we upload it to Lambda and it just runs. And this is actually the killer one. Really pay what you use pricing. So generally these solutions runs like sometimes once per month, or very specific time slots of a day, like at night for 1 hour. But you still might not know when this function will be executed. There might be some times that it can be executed as well. So in this case, as we don't pay, if Lambda function doesn't execute it, we don't pay for it, and so it's just extremely good for the pricing based, considering the pricing. So this is one of the custom solutions we have. In this use case, we are integrated with log entries. So OpsGenie can trigger other API endpoints by using OpsGenie webhooks. For example, a new alert is created or acknowledged, close, or other alert actions. We can trigger API endpoints. In this case, we trigger an API gateway endpoint, and this API gateway endpoint is connected to a Lambda function. And what this Lambda function does is to query log entries API and get the related logs, and then attach it to by using our API, attach it to the alert. And so this is extremely important use case because you have all you need on the alert immediately. You query the data. You don't have to go to log entries. Query by yourself, and get the. Basically, you have the actionable alert, immediately. And this is a custom solution for our customers using log entries, for example. We use Lambda here. So another custom solution we have, it's like some of our customers wanted to create alerts from the messages sent to a Slack channel. So they are sending messages to Slack channel, they are writing a message, or other services sending messages to one Slack channel, and they wanted to create alerts from these messages. Maybe not for all, maybe they want to filter some of them, and get data from somewhere else. But in this use case, we also have this implemented on GitHub, so you can just look at the source code. It is like 10 lines of code. And we get the data from the Slack by using something called outgoing webhook triggers. So Slack has something called outgoing webhooks. And Slack triggers our API endpoint for each message sent to a channel. So we get the data in our Lambda function, and this Lambda function can filter the messages or get data from somewhere else, and they enrich the alert and create a new alert by using our API. So the last use case I'm going to talk about is service and incident management. Actually, this is the biggest one. This is a fully featured project, let me say, written in serverless architecture. It should be on production today. I think they are opening it for beta for some of our customers. So it is not like the other ones. The other ones are like plugins. They are connected to DynamoDB streams, doing some internal jobs. But this is a project directly interacts with customers. So I need you to focus on this part again. And there are some Lambda functions we have. This feature this service called service and incident management. We have entities like service alert, incident, and service. These are entities we have, and these Lambda functions are called by using AWS Lambda's SDKs. We don't have API gateway endpoints in front of these Lambda functions, we have we are calling these Lambda functions using Amazon Lambda SDKs, but we are not using the Lambda SDK in our applications directly. But this our service and incident management team provides an SDK and abstracts away some of the internals. And by using the SDK provided by the service and incident management team, our applications can trigger these Lambda functions and execute service and incident management workflows. And we have incident executor and service executors. These are synchronous, so these services need to handle the exceptions by themselves. But in alert case, it's called asynchronously. So if something happens, let's say we called it asynchronously, something happened, we get an exception, we put the data to a dead letter queue. Currently, AWS Lambda doesn't have SQS trigger, but we are maybe because of the nature of the SQS, but we are hoping that they will implement this soon. But to pull the data from the data queue, we have another Lambda function running, pulling data, and it's trying to execute again. And these Lambda functions connects to DynamoDB and Elasticsearch Redis as well, like our other applications. And all these runs in a VPC container. And to access DynamoDB, 2 weeks ago they announced DynamoDB VPC endpoint, just like S3. And I think we are going to use it. But currently we have VPC Net Gateway and Internet Gateway, configured to access DynamoDB within VPC. It's just the same EC2 case, same in the Lambda. And our Redis also is in the VPC container, so we can access directly. And we have a Lambda function called format Lambda, and I will talk about this in detail. I think 2 slides later. But what it does is basically it tries to keep a specific number of Lambda functions running. I will talk about the reason and the detail soon. Just remember this: we have a format Lambda function called format Lambda, and it interacts with all these Lambda functions. So another problem that I'm going to talk about soon is monitoring. Monitoring of these Lambda functions is a little bit problematic because, for example, in our EC2 machines, virtual machines, we are using New Relic, and you can pass the JVM parameters, attach a New Relic agent. But in Lambda case, you don't manage the runtime environment, you cannot do it. So we have some solutions for this. We have our own auditing mechanism. Basically, it records all the for each function, it records all the upcoming data and return data and the execution time, etc. So a very new service, and I think we are going to use it. It looks like it's extremely useful, and I will talk about this again. And we put our data, both our custom logs and our auditing logs, to X-ray, and we are sending this data to, of course, Lambda functions automatically sends this. If you write a log, it sends this data automatically to CloudWatch. So from the CloudWatch, by using CloudWatch trigger, we get data. We get this data in monitoring Lambda, and this Lambda puts data to New Relic. So we want to use New Relic's querying capabilities, like their language, like New Relic query language, is extremely useful. And we also put data to Firos, from Firos to S3 and Elasticsearch again. So the challenges we face with AWS Lambda can be, I categorize them into 3 parts. First one is Java cold start time. Second one is proper monitoring, and third one is deployment. So what is cold start? Lambda functions, run inside of a container, and languages like Python or Node.js do not experience this cold start a lot, like in Java, because of the nature of the Java language. Because of the JVM, it loads all the classes, class loading time. if you if Lambda creates a new container, there is a class loading time generally caused by the class loading. And in our case, if we do not run all the auditing mechanism, it takes like, because we are also running Spring framework inside of Lambda functions, it takes like 3 seconds. But again, this cold start time happens only when a new container is created by AWS Lambda. It is transparent, and if you are calling your Lambda functions frequently, it is very rare. You don't generally encounter this cold start time, but you still can and will. So you need to be you need to take some sort of actions to decrease the number of the chance of experiencing cold starts. So for this, we have something of, as I showed you earlier, warm-up Lambda. What it does, every Lambda function has some sort of configuration parameter attached to the as an environment variable. So this Lambda function knows how many Lambda functions need to be up and running concurrently, and queries the Lambda functions and gets the environment variables, etc., and tries to have the number of let's say 2. It tries to keep two concurrent 2 Lambda functions up and running. So in this case, for example, we call it no operations. When we call these Lambda functions, they don't do anything. They just if there's no container running for these Lambda functions, basically by calling these Lambda functions immediately 2 times, it creates a 2 container. We have internal logic to know how many containers currently running, and I don't know the details for this one, but I think they are blogging about this. They will publish this blog post, and I think we might open source this one as well. So it's extremely we are not in production yet, but reduce the number of times we experience cold starts for our functions, especially. But you can and we will still experience these cold starts, especially if you are using Java, and if you are under some sort of SLAs, basically you cannot use serverless architecture for this kind of things, and because it doesn't guarantee how long the cold start time will take. So another problem was protocol monitoring, and as I said earlier, we want to use numeric capabilities, and so we are sending our logs to the AWS X-Ray and CloudWatch automatically, and from CloudWatch we are writing the logs to the numeric and Elasticsearch. So Amazon X-Ray, what is X-Ray? Basically, it provides end-to-end waves of requests. So both for the Amazon's internal services, it does this automatically. So if you are using, let's say, DynamoDB, it automatically records how much a request to DynamoDB takes, what was the payload, etc. I will show you some screenshots from the service as well. Also, you can integrate this with your own services. So in our case, we are integrated X-Ray with our own auditing system, and from one view, it looks like this. We have different, processes or functions called and logged to the X-Ray. It shows if an exception occurs, how long the call takes, etc. So in this view, we integrated our own services, our own auditing system with X-Ray. If we use we can use X-Ray's SDKs to send data to X-Ray, or if you use their provided HTTP client to access some other external service, it automatically records the how long the request takes, etc. by tracking the some sort of ID attached to the header of the request. And this is extremely useful because it even shows how much a function or service takes. I think we are going to use this service a lot. So just so we are doing blue-green deployment. So in blue-green deployment, you have two versions of your applications up and running at the same time. So as we will have two versions of our applications running. We need to call the proper Lambda functions by. We are using AWS Lambda's LI support for this. So different versions of our applications can call different versions of AWS Lambda functions by using their LIs, basically. We are leveraging LI support here. We are blogging about, we have 4 or 5 blog posts about serverless in our blog, engineering.oficinas.com. And after today, we have like 8 more coming. And we are thinking about open sourcing some of the internal tools, like our auditing mechanism for AWS Lambda. It automatically gets all the data, collects the data from the functions and tries to extract some other services, etc. So just a little data advertisement. We recently launched our playground environment, so you can go there and try different tools like Jira, HipChat, Nagios, Datadog, Slack, and how OpsGenie fits your use case and how we integrate with these tools. It's all set up. You can just go there and try these tools and create alerts and get notified, etc. That's all. If you have any questions, if you have time, you can ask now, or if you don't have time, you can talk later. Yeah.
So with all this much of Lambda you're using, you've never run out of concurrency. You hit the limit.
No. We didn't probably because we are we are starting to use the incident service management today. So in production, maybe we can run to the limit, but they are increasing this limit a lot. So we didn't encounter the limit before. But for the DynamoDB cross-region application case, we pay a lot because all the records came to DynamoDB tables. Of course, they are triggering the Lambda functions as batch, like 20 records at once. But still, we pay a lot compared to regular EC2 machine. But we don't have to think about the scaling. If something is wrong, it's not our problem. So it works.
Yeah. So X-rates is fed with the logs that your application produces?
Yeah.
Or?
Yeah. By default, it is integrated with other AWS services like DynamoDB, S3. You make a request to other services like Elastic Redis, Amazon Elasticsearch Redis, or S3 or DynamoDB. It automatically records to check the time, the request time, etc. But in our case, we can we are able to integrate with our own auditing mechanism, send data to by using their SDK to extract, and see all the DynamoDB calls and our internal codes in one view.
Elasticsearch.
Yeah, you can do it.
No,
can,
are you using that one?
Yeah, we are using
Elasticsearch?
We are using Elasticsearch together. Sure.
Do you have to warm up any functions that are stateful, like they change the state of your system? And if you do, how do you avoid making unintended changes just to keep the function warm?
So can I get the question?
So for example, if you have a function that inserts a row in a database, you could send a dummy row
Okay.
to keep it warm,
as
but
I
you
said,
don't want that data.
Exactly. As I said earlier, there is something called nodes. We specifically send some sort of payload, and functions know that they shouldn't do anything with the payload. they know which Lambda function calls them, and I didn't implement this one, but my friend told me that they called the Lambda functions with specific parameters, so the Lambda functions know that they shouldn't be doing anything.
So you have like a debug on sort of parameter.
Yes.
But those functions are run on BBC. The ones you're warming up are run on BBC. Are you making some network requests from the Lambda when you're not doing a no-op? Because you're supposed to have a penalty when you initialize a new network interface for the Lambda in the BBC. It's maybe even higher than Java startup.
I'm not sure. We can ask can't operator, but ask we can ask about my friend who implemented this. I don't know.
Well, just wanted to share it's an issue that I faced recently because I trigger Lambda function through S3 object. Once object is stored, Lambda function is triggered. In case that Lambda function is triggered several times because the object is stored on several data centers. So it's this was explanation that AWS support
Double more than one time, right?
Yeah.
Yeah, your functions need to. I don't.
Not because of the execution failure, but
Exactly. We talked about AWS about this, and they said that they can call Lambda functions more than once. They are not they are not saying they are strictly called these Lambda functions. What you need to design your functions accordingly. It might be a problem, but you need to think about the possibility of calling the same Lambda function twice from any other from all resources.
Theoretically, it's possible.
Yes. Practically,
practically
we experimented as well. Yeah, it's possible.
When you develop, you develop using Git, and then you do commits to Git. And when you develop, what's the environment? You use Git commits to get to Lambda some.
Yeah, I couldn't hear.
To do the versioning, when you develop new functions and everything, what do you do the versioning? After in Lambda or
we are doing the versioning and AWS in Lambda. Yes.
But we didn't use Git or anything, and then you go from Git to.
I think we are using a feature of serverless JS, to update the AWS or the version. Again, I'm not sure about the details because incident and service management only uses this feature for now, and they are using AWS Lambda's AWS support for this. I think they are updating their license using serverless. If I didn't answer your questions exactly, we can.
I found it difficult to work with Lambda when I tried to do the thing. It was not like.
We are putting some, let's say we change the Lambda function and we want to use different version. We deploy the Lambda function with different allies and call the Lambda function that allies. We can talk about the details,
Maximum, something like that. They were like strange limits. I don't know. Maybe we're talking about.
I think we didn't, experience any problem with this, but I can direct to my friend working on this and ask if they have any problems with the versioning or the license. But as far as I know, it works with the different versions of the Lambda functions for calling them from different institutions, different applications. So if you're I brought some Turkish slides. I'm from Turkey, by the way. I don't. If you don't have questions, you can
Are we gonna make like 5 minutes?
Yes, 5 minutes. Let's do a 5-minute break, and we have here some Turkish sweets that Serhat just brought from Turkey. So let's try it all together.
There will be a slide.
algo por aquí, ¿no?
Sí, estem fora d'horaria.
You need to plug into your USB. And it works. Yeah.
Què tal, Gerard?
Molt bé, com estem?
Tranquil·litat.
T'està parlant amb el Jesús l'altre dia.
Sí?
Va dir que estava content amb vosaltres.
Això espero.
Esteu contents amb ell també?
Sí, home.
Well, if there is another one there.
No, but that one, it doesn't, it's not long enough. No? No, it's not, it doesn't work. Don't worry. Let's hope.
No, the touch twice are running out. You can.
I already know. I'm gonna take one.
Yeah, go for it. So you are going to do the presentation in English, right? Okay, nice.
Really good.
Voy a arreglar esto, es que en esta una demo, tenemos una demo de lo que estamos haciendo y hay uno que no está con otros tasks que es propietaria y esto está a medias, bastante peor de lo que pensaba. Y le has dicho, que funcione y tal, para que ya estoy viendo y se hacen un montón de cambios. De momento no tienes complejidad añadirle a capa. Por ejemplo, tiene un proyecto que tuvieron un prototipo de izquierda anteriormente. Metieron reglas en ese principio y se ve que añadir una complejidad innecesaria para lo que se tiene que hacer.
Tienes muchas cosas que mantener el estado, no tiene una cosa que la otra, extracción,
Hay componentes de funciones que
Okay. Around 30 minutes. 30 minutes. Shall we ask people to come back?
Yes.
Estamos fuera. No, díselo aquí, en cambio.
Sí, he posat l'altra cadira allà al fons, per si vols. És que la gent que estava online m'estava dient, no?
És que veu tot el món envoltat, sí, sí.
I llavors he dit, només
Deixa'm aquí.
la cadira ja no serà per res.
No, no.
Sí,
Okay. I'm gonna start with the second presentation of today. My name is Radek. I work at Skyscanner. I'm a software engineer. And I'm gonna talk to you about the data processing without servers, or without knowing about servers, more like this. And AWS. This is gonna be also a walkthrough through our use case. With hopefully we're gonna share some learnings that from the challenges that
that we faced, and hopefully it's gonna be something applicable to your job. So to start, in my team, one of the services that we maintain is the autosuggest. Autosuggest is the service that is responsible for feeding these boxes here. So whenever you type any letter in the from or the destination box, what you see on the drop-down comes from our autosuggest service. And in order to show you something on this drop-down, we need to have data. And as Skyscanner is a travel company, we have our internal representation of the world. So all the places, everything we know about the world, all the names, we have it in our representation of the data of the world. And all those names are in 42 languages, the languages that we support, so that whenever you look for something, hopefully we're gonna show you on the drop down. But this data and the format of this data that we have doesn't allow you to quickly search. So we have to process this data and produce the indexes and some metadata files so that your response and the drop down, the suggestions that you see are showing up almost immediately. The process of creating those indexes, we call it indexing because it produces solar indexes that we use to serve the data, is a quite heavy process. It produces around 100 gigabytes of data. It takes several hours to complete. The process running in the data center was historically running in the data centers, but as a company we grow quite quickly and we had to scale it, which was not possible in the data center because of the constraints. And in order to scale, we needed to do something. And the something was to migrate it to AWS so that we can leverage almost infinite resources. So when we were thinking about migrating, about implementing it on AWS, because obviously we didn't want to do the lift and shift, so just copy everything and run in AWS because that won't bring us anywhere and that would cost a lot of money. So apart from the scalability, that was the first requirement that we had. That was the second one was the effectiveness. So that because as I mentioned, the process is quite heavy and it uses a lot of very big machines, we didn't want to waste them. So whenever there is a task to process, we want the resource to be ready, but not before. And whenever the task is finished, we don't want the resource to be there anymore. So we don't want to waste any money. Automated, well, obviously we want the solution to be no maintenance solution. So we don't want to spend time triggering it. We don't want to spend time analyzing anything or copying data across. We want everything to happen automatically. Another requirement was coordinated, which means for us that we have a hierarchy of tasks and we have dependencies between them during the whole process. So we wanted a solution we needed a solution that would allow us to configure the dependencies, and so that we don't have to, ideally, we don't have to set up anything manually managed, which means that we want to leverage as much as possible. So we want to create it on top of AWS, leverage services so that we don't reinvent the wheel. And also at Skyscanner, we have a lot of internal tools available, so we wanted to leverage as much as possible. And compatible, this is a kind of nice to have one. So because we have a historically the process was in data center, so we would like not to rewrite the thing. So as much as possible, we would like to reuse that code, obviously with redesigning the whole architecture. If you look at those requirements from a little bit different perspective, you end up with something like this. We need an orchestration layer that allows us to set up the dependencies between the tasks, and that will take care of managing which task is ready to run, which task is finished, so that possibly some others are ready because they were depending on that one. So this is the layer that we need. And another one is the resources management, because we don't want to waste any resources. So we want something that will take care of it for us. And resources management, it's pretty much what serverless means. You don't have to worry about servers. It doesn't mean that there are no servers, but you just don't care. Whenever server is needed, it's gonna be there. If its job is finished, it's gone. So we know more or less what we are looking for. Here is like a very high-level overview what we are aiming for. So you see, this is our famous indexing process. We have stuff still running in data center that will produce some input. This is the S3 bucket, right? So there is some input. We're running the magic process inside. It produces output. The output we need to replicate to different regions because we serve it from different regions. and apart from this, we want the whole process to be automated and monitored. So we have some monitoring and notification. Well, we need to see what's going on there, and we need some control. So in case anything goes wrong, or in case we want to trigger something manually because of an error, or for testing, we want to be able to do that. These were our requirements. Then, with those requirements, we looked at AWS, and we looked what are our options to implement that. So, well, first one, using some batch processing, you could just wrap it into the container, throw it into the ACS, you would just execute it, and whenever the job is finished, the container will be removed. And apart from that, we have internal tooling, so that was very tempting for us to just use ECS. But then, if you start thinking about it, you see that, well, ECS is very nice service, but still in instances that are running inside the cluster, they need to be managed somehow. And especially if you need to scale, you need some custom solution there, which maybe in some of your companies you have a company-wide cluster. So in that case, it's not a big deal, probably. But on the other hand, you need to take care also, and you need to make sure that the tasks that you're going to throw at the cluster, that there's going to be resources. Because in our case, the tasks were like 40 tasks that required 30 gigs of RAM each, so that's not going to be that much spare resources on the cluster. So whenever you throw at it, they will need to wait to scale up, and then when you finish, before the cluster realizes that those resources are not being used, it will also take some time. So you're gonna need to once set up the whole scaling, and then you're gonna probably waste some resources. But even though these are kind of inconveniences that you could work around, then another one, the orchestration requirement, it's not fulfilled at all. We cannot set up the dependencies. So to run one task and another one wait for it, we will need to set up something custom. And because ECS just doesn't provide it at all. But since AWS has a lot of different services, then there is simple workflow, which is exactly what we need. There is orchestration, there are task dependencies, you can even run code in between tasks so that they can be totally separated. You can map your data format between the tasks. And during the November's reInvent there was another service announced that even simplifies that process, which is called step functions. So you don't have to run the decider, the main process anymore. It's run by the AWS, and you then have some visualizations, and you can see how your process is looking like, which is pretty much what we would need for the orchestration. But still, this is the service that does the orchestration. The other one runs our code. So even though it looks like there is a good fit, we kind of weren't very happy with that because we would need to integrate it. We would need still to manage. So all the inconveniences with ECS and scaling, they are still there, and we have two services. So it's a very valid option, but we kind of explored further, and we arrived to the data pipeline, which kind of does both the orchestration and the resources thing at the same time. So it will take care of provisioning. It will also allow you to set up the hierarchy of the tasks. And apart from that, it has a couple of very handy features like built-in retries, so you can just say how many times you want to run your task, or support for S3, because as you've seen, our data input data is in S3, and output we also want to put in S3. So that's gonna be handy for us. As a disadvantages, there is no Docker support. Like data pipeline is quite old service. Docker was not too popular probably, or just this version, it didn't arrive to add the Docker support. But we didn't need Docker support at that point. We could easily do it without Docker, so it looks like it's a pretty good fit. Data pipeline at this point. But well, as with AWS happens quite often, they just announce services without telling you before. So together with the function, there was an AWS batch announced, which does most of the things that the data pipeline does in kind of more organized way. So you have the resources provisioning. You also have dependencies within the tasks, which are called jobs in this case. So you can set up that the job depends on another one. It will wait for it. There is also retries. There is native Docker support. So you just specify where to get the Docker image from, and it's gonna run it with the parameters you want to pass to it. Well, nothing is perfect. So batch is only in Virginia at the moment. And there's nothing built in for S3, so you need to make our tasks aware of where the data comes from and where to put it back. And there are some limits, like 20 job dependencies, which kind of is not enough for us. But yeah, these are the things that you could work around. At least main requirements are fulfilled. So if we evaluate everything, what happens? Well, I added another requirement in the end, which was that service is available, and the batch was not available when we were evaluating the thing. So it kind of didn't have a chance to win at that point. And if we look at data pipeline. So this yellow one, I put yellow because the requirement, the feature is there, but it's kind of not full. So you need to make some effort to make it to fulfill it. So in case of ECS, it's gonna be effective if you put scaling properly. There's no orchestration, so we don't have that. But the managed, so well, the AWS service, there's a lot of internal tooling. In our case, so that's gonna be helpful. Compatible, well, it's compatible with our code because you can wrap anything into the Docker container. So as long as it can be running the container, it's gonna run on ECS. And yeah, it's available. We can use it right away. Step functions and the simple workflow, well, it cannot be effective because there's no resources. There's orchestration. it's managed because it's a AWS service, but we would need to make some effort to run some automation around. There's no resources, no code to running by the step functions themselves, so there is nothing to say about compatibility and availability. Well, at the data pipeline, if you look at it, everything is fulfilled, so we decided that we're gonna try it because it looks like it fits. So we tried, and well, we faced a couple of challenges that we're gonna talk about. Hopefully, it's gonna be something applicable to you. We started defining the pipeline. What do you do to create a pipeline? Well, we realized that there is a massive JSON to create. The pipeline definition is a very big JSON. All the fields are just pretty much key and value, so there's like a big list of properties, and it's very difficult to create and to kind of analyze what's happening there. So fortunately, there's a pipeline architect, which is very far from being perfect, but it does allow you to kind of validate your generated pipeline if it at least it's according to the schema, and it can display some visualization, so you know more or less how the flow is going. And that's what we used a lot, to use the architect and then export the as a definition so that we can see if our generated one matches it, because yeah, we didn't want to, we wanted everything to be automated, so there's gonna be something that will generate it automatically. And apart from the pipeline, another thing that we decided to do because of the complexity of the pipeline definition is to abstract it through the service API. So the API is gonna contain all the complexity, all the logic that is required to create a pipeline, and the client will just throw 3 parameters saying what kind of data you want to index, and that's gonna be it, and the API will take care of it. So this is fine. We have our API, we have our logic to create a pipeline, and then we try to start it. So we try to start it, and nothing happens. We see timeouts. We wrap it with the API, we call the API, and we see timeouts, and then we realize that the pipeline can take a long time to initialize, especially if it's big. So there is a lot of tasks and there is dependencies between them. And since we use the API gateway to abstract the whole thing, it has the hard limit of 30 seconds for the timeout. And when the pipeline creation takes a couple of minutes, then it just times out of it every time, even though the pipeline is being created fine, but your request times out. So that was kind of unexpected. What we decided to do is to run Lambda synchronously. So in the end, Lambda, the pipeline creation happens in 3 stages. So the pipeline creation, normally from the AWS point of view, are 3 steps. So we have creation, we have definition, and we have initialization. So the creation is super simple because you don't put any content. So you just say, okay, create me a pipeline. And that's super fast. Then we have the definition. So you just have the ID of the pipeline that you just created, and you just push the definition that you generated, so the whole JSON that we were talking about before. And that can take time. I imagine there is validation going on if the whole thing is correct. And then another one, which also takes some time, is when the pipeline is defined, just push the trigger to start it. So we decided to run only the first part synchronously. You get the response quickly, and then we asynchronously initialize the whole pipeline, which was fine. Obviously, the problem is that if the first call pretty much never fails. Empty pipeline you can create anytime, but if your definition is bad, you're not gonna know about that in a synchronous way. So you need some kind of notifications reporting from those pipelines in place, so that you know that your pipeline doesn't really work. So okay, we fixed that unexpected issue. We managed to start our pipeline, and then we don't see any logs. Where are our logs? We configured the pipeline to upload logs to S3, but they are not there. The pipeline seems to be running, but it's not writing anything. So we don't really know if it's working or not. So apparently, the logs of the data pipeline are being uploaded to S3 with sometimes up to 20 minutes delay. So yeah, when it crashes, you're probably gonna see earlier. But if it works, but let's say it's stuck, it's not doing anything, you're not gonna see it. So how would you solve that? Well, we thought we just have another process in our task. They will just forward the standard output. What's printed to the standard output, we forward it to CloudWatch. You can imagine using any other logging solution, and in this case, you're gonna get it immediately, and then you just treat the S3 logs as a backup. So yeah, another unexpected issue. We got it solved, and then we think, how do we tell the pipeline what to run? We have some input, we have some code. Our code has a lot of dependencies. We need to install a lot of libraries on the machine to be able to run our code. And well, we have a lot of options. We can just use a regular EMI, have a script that will pull everything from somewhere, from S3, from some Artifactory, wherever you store your artifacts, and then install on the machine, and then run your job. But that means that you're gonna spend a lot of time preparing your machine to be ready to process your data. And we want it to be effective, so we don't want to spend time doing this thing all over and over again. So we decided that dependencies needs to be in the EMI. That means that we need to have a process for creating an EMI with the dependencies. So whenever the dependencies change, we need to rebuild an EMI and tell our API that from now on, whenever someone wants to create a pipeline, use this new EMI. What we ended up doing is having, as I mentioned, dependencies in the build time. So we put it inside the EMI, and then code and the data, that's input data needed to be processed, we're gonna fetch it during the runtime. So we have the data on S3, we have code in Artifactory, our artifacts, and we're gonna fetch it. It shouldn't take too much time, and it's kind of easier, at least at the beginning, to not to manage another process for taking EMIs every time there is a release, code release, data release, having EMIs with everything backed in. But yeah, we kind of realized that that would probably improve our processing time. But that's what we started with, and yeah, that was kind of working. But for the dependencies part, we had to kind of knew wherever the change that we are introducing to the process, is it gonna affect the base or not? Do we have to rebuild an EMI? And it kind of introduces some complexity, and then because of this serverless approach, it was kind of difficult to test the whole thing on your development machines, especially that our process had a lot of dependencies. You couldn't just install everything locally and run it. That was very complicated. So we thought, well, maybe we could do something, and we could kind of kill two birds together and then package it all together, and also allow us to easily test it locally and develop on our machines by using Docker. That's what Docker allows you to do easily. But then, but we decided that we actually didn't need Docker, and we don't have any Docker support in data pipeline. What can we do about that? Well, we are using shell activities. So in data pipeline, you have multiple kind of activities. You can run some SQL, export data from Dynamo, and you can just have a generic kind of thing called shell command activity that allows you to do pretty much anything. So we decided that we can install Docker on our EMI, and Docker, and that's it. And that means that we're not gonna change it pretty much ever. And then passing the command, tell that we want to run Docker. So data pipeline doesn't really need to know that it's running Docker, but it's gonna be running Docker. And so we wrapped it, created some scripts to wrap the Docker commands using the shell activity. And this advantage of having the built-in S3 support was super useful in this case because we could map the directories from the machine to the container so that it's separated completely and the container doesn't know where the data comes from. So you could easily run it locally with the same container, the same image, using some your test data or your generated data some other way. It doesn't come from S3, and the output you don't want to put to S3 for testing purposes or for developing, so it's just gonna write to local disk. And data pipeline will just take care of uploading it back to S3 to the bucket that you've specified. So yeah, another problem solved. It's fine and everything is running, but we don't see how it behaves. So we've put some instance types. We know that we see in the console that there are some instances running, so we kind of assume they come from data pipeline, but we don't know which instance runs which task. We don't know if we chose the instance types properly, if the resources utilization is good, if we are not over provisioned because we didn't want to waste any money. We also don't want to be under provisioned so that our processing takes longer than it should. So we had to do some manual work to work around this, and what we ended up doing is sending the metrics manually. So next to the Docker process, you're gonna have another one that will monitor your machine, your instance that the container is running on, and we're gonna send the metrics from the machine, either to CloudWatch. In our case, we're sending it to the OpenTSDB, and then you're gonna set up your dashboards using that data. So yeah, we have everything. Everything is running. You have your metric, you have your notifications, and your data is being pushed to the S3 bucket. But then, a couple of weeks, you may encounter a new problem. That you face some limits. Like they said, cloud is infinite, but then you cannot provision an instance because there is no EC2 of this type available. And then, yeah, what you could do, you cannot do much. You're not gonna go to the AWS data center and bring new server. So what you can do to mitigate the issue is, and you should do also for other reasons, is make sure that you provision your instances in different availability zones. You can actually provision them in different regions because data pipeline, even though the orchestration layer is running in a single region, the instances may be spread. So to make sure you're not gonna use all the resources in one availability zone, make sure that you're spreading that across different ones, so it's less likely to hit the limit. And apart from this limit, like resources limit, you're gonna reach some other issues with data pipeline limits, which are easier to fix because there are just limits on AWS. So you're gonna have like number of objects per pipeline limit, and then most of them can just raise by filling a ticket to the support. So yeah, we have our solution now. We're gonna look back and see if we made it, if it fulfills our requirements. So yeah, scalability, it's fine. If we need another partition and more data to process, we just put new task in data pipeline. You can like create a node instance to process the data. It's effective, but it's hard to be more effective where we're not having instances not doing anything at any point of time. So you have the task, it's ready to be run, data pipeline, create an instance, process the task, and shut down the instance when the thing is finished. It's automated. Well, that requires quite more work with the API, gateway, with the Lambda, but it's there, so we did that coordinated. The hierarchy of the tasks, the data pipeline allows you to do that, so we leveraged that, and it works fine. It's managed. We don't worry about the service. We didn't have to reinvent anything. Just using the services provided. We had to. There's no calling in Skyscanner for that, so we had to build some stuff on our own, like for metrics and stuff. But it's there, and it's compatible with our code because we wrapped everything into the Docker containers, and we didn't have to rewrite almost anything to use the same code that we were using before, even though the architecture is completely different. And what's more important, it's serverless, so we don't worry about servers. And if you look, I don't know if you probably can't look at, I can't see anything, right? Oh. Oh, sorry. Can you see anything? Oh, I will explain. So this is the main part. So you have the local containers and the data pipeline. And there is the API that I mentioned before, the control part that we said that we need. So in case something goes wrong, we have a Jenkins job that will just go through the same API that is used in an automated way from the data center, and you can trigger stuff as the same way as that would be done automatically. We have Grafana, so the dashboards that are querying the same API, so that we can see the state of the executions. And we have Slack bot that will also query the same API, so that we see how many pipelines, what are they doing, are they finishing, are they stuck, or whatever. And then we have our input data that is pushed from data center. Whenever the data is pushed, the automated process will call the API, and the API will call Lambda, which will create a data pipeline. Data pipeline will spin up some instances and put some containers on them. Containers will just fetch data, fetch the input data, do the processing, and output something to the output bucket. When the output is finished, it was our requirement too. We want this data to be replicated across other 3 regions. So there's gonna be, this is the dependency thing that we needed, so that this needs to be finished before this guy comes into play. So when the data is there, he will pick it up and copy it across two buckets in different regions. When the pipeline is finished, the SMS notification is sent, and we see this also on Slack. The notification that the pipeline has finished. Of course, in case it failed, you also notify and bring the error from the last failed command. This is where you can see it in practice. So this is one of the graph in our dashboard, and you can see that this is the ID of the pipeline that we were starting, and there was nothing before. At some point, it created one instance because we had the first kind of a pre-processing stuff. When this finished processing, it spin up like 18, I think it was, instances to process this data, so different partitions or different nodes in parallel. They were finishing, they don't take exactly the same amount of time, So they were being shut down gradually. And then in the end, there is another instance to do some post-processing and copy the data across to different regions. So at this point, all those instances were already shut down, and when this one finished, it shut down the whole thing and we moved to the pipeline. So this is how it works. It works fine. To summarize, we had to, as you saw, we had to face a couple of challenges, but thanks to data pipeline, we met all our requirements. Everything works fine. Unfortunately, there was no AWS batch at that point, so we would probably, if we were to start again, at least we would look at it and closer and see if that would allow us to avoid some of the issues we had and some of the problems we had to solve. But still, data pipeline is a valid service to take a look at, especially that there's a couple of stuff that batch doesn't give you, like this S3 built-in support, which allows you to nicely decouple code from the data, and stuff like being able to provision instances in different regions at the same time, which in batch you have a pool of instances that run your containers, and they are all in the same region. There are also some limits in the batch that potentially would hit us, and we potentially need to somehow work around them. But yeah, works fine. No serverless. Hopefully, some stuff from this presentation is gonna be applicable to you. Thanks a lot. Questions?
What is still running in the data center? It's still in the diagram.
Yeah. So when there was this, what happened? So there was this our representation of the data, and some part that is actually fetching from those databases has to run in data center because the data is there, and we could in theory query it from the AWS, but that's gonna take so much time. But for now, this part that's actually reads the data, pushes it to S3, it's in data center. Yep.
So why are you copying from bucket to bucket as a step on the pipeline, and not replicating with the built-in function of S3?
Yeah, because that's faster this way. So we investigated different options. We could have replication, like built-in replication, which is, and whenever you put a file in one bucket, you copy it to another one. So in our case, we need to copy to 3. So we would need to change them. Another thing is that we won't really know whenever it's finished. We will just do it transparently, and we need to know that our processing is finished and we are ready to deploy in all the regions. So make sure that data is already there. There is also different options to do copying, like you can use the Amazon client and say sync with this bucket, and then you don't need any instances. But still it was slower. So the fastest option that we found was provisioning an instance in the particular region, fetching it from different, like in our case we have data in Ireland, so we provision instance in Tokyo, fetch from Ireland using the accelerated buckets. So this is like a S3 feature, and push it to the local bucket, which is very fast. So in this case, we can, in like 20 minutes, we can replicate like 50 gigs of data or something. So yeah, that was the reason. No more questions? Thanks.
Sorry. Thank you, Radek.
So you push the logs